All right, so yes, we are studying two methods for each approach in the book. There might be a little bit, maybe one more. I'm only, as resorting to two approaches here. Open method. Why it is called open method is, let's compare this with the bracketing method. So in bracketing method, so let's say you have a function, and then the root is here. Even if there's a second root, we don't usually worry about it. Yes, there will be a question about Taylor series because it is lecture 4, right? So in bracketing method, what we do is we give a bracket and then say XL and then XU, and then we have two different methods. We studied two different methods to find the root. One is the bisection method. One is false position method. Now, similarly here, why this is called open method? That we don't say there's we don't know the upper lower bounds of the root. So let's say the root is here. I want to show the second root. There might be one. So let's say this is the root. That is the root. So we start at some point. So we will start at some point, x0, and then iterate. So there is no bracket. It is open. So how it works, that's what we are going to study. So that's the first approach is called fixed point iteration. The second approach is called Newton-Raphson method. So these are studies now you know the drill about these lectures. I will there is a concept, most of the concept that you did not know before. That's why all these lectures fall under computer-aided analysis. So how we use computer programming to solve different kind of problems. I'm introducing different kind of solution approaches and also showing examples in homework question, mostly some example relating to where this will be applied. So most of the remaining lectures will be like that. We'll introduce some concept, and I will also introduce for each method the algorithm will be there. Most of these algorithms, not all of them, you will program in the lab these algorithms, and then this time you'll also do this algorithm at least during exams. Okay, so for fixed point iteration, we write the function. So we always want to solve fx is equal to 0. That is what we want to solve, but that can be written in this form. X is equal to gx. I will give an example. If you can write that function, and a function fx is 0 in this form, then that is an iteration right there. This is a present root, and that is the next root. For example, let's say we have to solve x squared minus 4x squared minus 3x plus 2 is equal to 0. Let's say we have to solve this. So if I have to write that in x is equal to gx form, I will write 3x is equal to 4x squared plus 2. X is 4x squared plus 2 over 3. Now, if you look at it, that is in x is equal to gx form. So I will start with the initial guess. So let's say initial guess is x0, and then x1 is 4x0 squared plus 2 over 3. And then x2 is 4x1 squared plus 2 over 3, and so on. So you can do this iteration and then compare it with, we can find the real root since that's a quadratic equation. So that's a demonstration of that approach. So then we will, everything else is kind of the same. We'll compute the percentage relative error, and then we will stop the iteration until when the error becomes less than a small value. Now, before I go into the example, let me know. So that's a comparison, open method in comparison with the bracketing method. So okay, that figure is nothing. You can, okay, this is the figure I want to discuss. So x is equal to gx, x is equal to gx. So xi plus 1 is equal to gxi. So you have a current guess for the root. The next guess will be just you submit it to the function. So let's say this is what I'm showing here. This is the function. This is the function that gx. This is a function. X is equal to gx is what we came up with from the original function, which was fx is equal to 0. Then, so if this is x0, if this is x0, and then gx is that place, that this is gx, this is gx. The next root is, if you just project that gx to y is equal to x, and then that is the next root. So why is that? Because root is always on the x-axis. And we know that if, for example, x0, gx0 is x1. So we found out that gx0 is here. This is gx0. This is gx0. So how do we know where is g1 graphically? Then if you have y is equal to x, so this is y is equal to x. If you have y is equal to x, what does it mean? It means if you have a point here, these two lengths are same. So that's what, because due to symmetry, that is y is equal to x equally divides that angle. So that would be, oops. So that would be 45 and 45, right? So if you have y is equal to x, it equally divides. So if this is gx, if this point is, the red point that I'm showing is gx on the graph, then if you just project it to y is equal to x, and this is going to be x1. So this is a graphical explanation of how it works and how it converges. So now you can see. So that is the next root. So once you have the next root, then again, that is gx1. So if gx1, you just project it to y is equal to x, and you find it's 2. So you see, we started at x0. The next iteration, it goes toward x1, because this is the real root, right? This is the actual, that is xr. That is where we want to go. We want to find the xr. So this works nicely, at least it graphically. It shows that, you just have y1 is equal to x, and you just project it to y is equal to n. Always, you see, if you look at the arrow, there's no way, wherever you start, it is always bringing you towards a real root after some iterations. So once graph A is understood, what happens here? Now we know the drill. You start with x0, find that point is y is equal to, gx0. So that is gx0. This point is g x0. So from that point, you will just project it to y is equal to x. So you project it to y is equal to x. So that is your next root, x1. And then you find that is g x1, and you project it to y is equal to x. That is x2. What is happening here? Yes, I mean, yes, I'm using the by value to project, but I hope I explained why that works. You know, I started here. I mean, well, let me review a little bit. So consider a function like this. So we want to solve this function. We want to find, so that's this function is something like this. This is a function something like this. We want to find these 2 points. Oh, forget about 2 points, or only 1 point. So because all the root finding method that we work, will work only for 1 point. So we are doing only very basic here, you see. So I can, the fixed point iteration, I can write it, the same equation in this form, and then coming to this form, and then I can just do this iteration. So here what I showed graphically is I showed here in the first one how the fixed point iteration works graphically. So you start with the initial point x0, and then you find gx0, and then you find gx1, and so on. So it nicely brings us towards the root, which is the one I just highlighted. So that is the root, the red one. That's the root. That is a root, because, so why that is root? Why that is root? Because x is equal to gx. So the intersection is the root, because earlier it was fx is equal to 0. If fx is equal to 0, then when fx touches x axis, that is the root. But when you have x is equal to gx, then when they both intersect, that is going to be the root. So the point I want to make here is that it is supposed to go towards the root. That is the root. That is xr. But this iteration just diverges. Every time you do this iteration, it just moves away from the root. So this is working as a root finding method, the application C. So the conclusion is it will only work for certain type of function. So that is what I want to say. But you know, when you review this, you will get that idea a bit more clearly. So now let me do an example that we have in the lecture notes. So here's another example. Okay. Okay, so fx is e to the power minus x, e to the power minus x minus x. That's a function. So as usual, we will write it x is equal to, we want to write it in x is equal to gx form. That is a fixed point iteration approach. So I can easily write it as x is equal to e to the power minus x. So if the first, so that is an iteration function right there. So I can write it as xi plus 1 is e to the power minus xi. So x1 is e to the power minus x0, x2 is e to the power minus x1, and so on. So that's the iteration. So here in this example, we are starting at x0 is equal to 0. That's our initial guess. Initial guess is x is equal to 0. So the first solution is e to the power minus 0, that is 1. So x2, so x1 is 1, x2 is e to the power minus x1, that is e to the power minus 1. So that comes to point. Did I make a mistake in my election mouse? So it should be negative, right? I'll fix that. Anyway, so I'm not sure if that affected the answer, but I will check that. You can also check. So the table one shows how every time you compute a, probably this comes from the book, so even though probably it's just a typo I have here for the negative, I don't think that it affected the answers. So because this example is from the textbook. Okay, so 0, 1, you see keeps going, and the error, percentage relative error, goes down as well. Whereas the true, you don't always get the true relative error, because to find the true error, we need to know what is the exact solution. So apparently for this example, the true solution is also given. True solution is probably, I did not write it here, but apparently I used it. So the true solution is known. I cannot tell you right now what is the value, but to compute this column, we need the true true root for this. Or other than that, we can compute the percentage relative error. And when you write an algorithm, the algorithm will only look at percentage relative error, because if you know the true root, why you need an algorithm? I mean, in practical application, we don't know true roots. Otherwise, we don't even need these methods. So that's basically the summary of this method. Now, let me quickly. Okay, so here, so in this algorithm section, I gave a brief, pseudocode for this algorithm. When you write this, you have to think a little bit more, because you cannot just translate this to an algorithm. But anyway, so our goal was to solve fx is equal to 0. So the first step is, this is not part of the algorithm, but first step is we had to write it in equal to x is equal to gx form. So if you are given a function, then you will just for example, if you are given that fx is equal to e to the power minus x, you will just write it in this form. And also you should know that there will be multiple ways to write that. So that's also another thing you need to keep in mind. That's why this can go wrong in many different ways. For example, let's take a look at this example. So I wrote it this way. I can also write it in, if I just take this, there's another way I can write 3x minus 2 is 4x squared. From this I can write x is 3x minus 2 over 4. I can also write that's also in x is equal to gx form. So which one will converge fast? That is beyond the scope of this course. Although our goal is in this course to introduce different methods for finding and show how to program it, and there'll be some question. Of course, I don't even think the textbook had that kind of explanation. But if you just take these two examples of how I did this one way, this is one way I wrote this. So that is in x is equal to g1x form. Here x is equal to g2x form. So in the same function, I also I started with a function called fx is equal to 0. My goal was to find the root of this function using fixed point iteration. I was able to write x is equal to g1x as well as x is equal to g2x. Which one is better? There are some tests to say that, for example, that's where this example came from. You know, the the derivative of this function, if you look at the derivative of this function around, if you have a good guess, so all these, most of the root finding method will only work well if you have a good guess for initial root. So that's always an assumption. You need to know the initial guess. So that's why if you look at all the example, we give the initial guess. For bracketing method, we give the initial bracket, because if you don't know the initial bracket, it's not going to work. So for this one, for open method, we need an initial guess. That is good enough. So we need a good enough initial guess. For the bracketing method, we need to give the brackets, right? I mean, last lecture 5. Bracket means XL and XU, lower limit, upper limit. And we are 100% sure, I mean, that the root is between those lower and upper limit. If that is not the case, our method won't give the roots. Same here, but at least here, there is no such condition, but it should be close enough. Otherwise, you will see it will diverge. And then another condition for diverging is, in this picture, figure 2, A shows a scenario where it nicely converges towards a root, and C shows a scenario where it diverges. If you compare the function gx in both these cases, the gradient of gx has the gradient is more than 1 here. So here in this case, the gradient more than 1 close to the roots. Here, gradient less than 1 close to the root. Why? The gradient of y is equal to x is 1. So if it is more than 1, it seems it is diverging. Less than 1. Again, that is not a rule that will always work, but most of the time it does. And here, another example of how it converges. So now we know how to graphically show. If I start x1 here, you find the function here and go to y is equal to x here, and that is x2. You go to, that will be gx1. So you go to y is equal to, and that is 2. And you go to the function, come back now. When you go to circular, you can see it just keep on rotating and going towards the root. The root is here. That's a root. But it's not. Here is another example. You start here, goes here, and goes back. It just keeps diverging. So, but if you look at that gradient, again, it is around the root. The gradient of the gx function is negative, less than 1. Whereas here, the gradient is greater than. So it is called a rule of thumb. That means it is not always true, but it is a good hunch about how these things happen. Now I will go back to the algorithm. Yes, gradient is same as derivative. Yeah. If you see a function, if I have a function like this, in every point there's, if this is x and if this is y, you can roughly what's the gradient, because we know that gradient of 45 is 1. Tan 45 is 1. So for example, if for example, if I have y is equal to x, and then around here, around this area where I highlight, the gradient is less than 1. Slope, tangent, gradient, derivative, these are all very related things. So the slope of the function around this area, for example, what is the slope? The gradient. Am I confusing you guys? You always okay, good. So gradient means if you know the function gx here, you take the derivative and give the value, and you will get the gradient at that point. All right. So I hope now it is clear how the fixed point iteration was. Very simple. The function, and you write it in x is equal to gx form. That is your iteration. You keep iterating it. So that is what I explained in this algorithm. So set I is equal to 1, and then xi, x raised I, that means the first root. So that is the first root. First root is our initial guess. So that is an input to the function. That is an input to the function. So then we will say xi plus 1, that is the next root, is dxi. So we need to know what is dxi. Now the error, so you have x plus 1 and you have xi, so you can compute the relative error. And then we check what is the, if the relative error is less than the threshold, so that is another input. Usually in for you in homework or lab, now we will give what's the threshold. So you check if it is less than that, then if it is less than, if the epsilon a is less than the threshold, declare the root as XR. So we are done. The iteration is done. If it is not, you go back to step 2. So this is the iteration. This is what we are going to iterate. So this is what you will iterate. Steps 2 to 4 is what you iterate. In C++, you will write a while loop. Also, in many questions, in addition to checking this, I already gave in some other examples in algorithm. I will also give a max iter. So sometimes, a good example is like this. Sometimes you will never converge. Sometimes you will diverge. So you don't want a program that doesn't stop. So it's always a good idea to, if you don't find anything within some number of iterations, you have to stop. That's always a good practice in programming. So I will also probably I'd like given it here, but in your lab that will be specifically given. So that's all for fixed point iteration method. So this is one of the open methods. Why it is an open method? We don't use a bracket. Now let me go to Newton-Raphson method. One of the well-known methods, very famous methods for root finding. Obviously invented by Newton. This is the formula to simplify things. That is the formula. I will come back and explain why, but compare that formula with the fixed point iteration. Fixed point iteration formula is xi plus 1 is equal to gxi. So much simpler for both of them. I mean, there's nothing complicated about both of them. So that is equation 20 is Newton-Raphson method. What I just wrote is fixed point iteration method. So that's a comparison. Once you know that, algorithm is the same. I mean, I don't need to re-explain algorithm for Newton-Raphson method. Same thing. Everything is going to be the same, except for Newton-Raphson, everything is going to be the same except for this step, the algorithm. So instead of that, you will have xi plus 1 is xi minus fxi divided by f prime xi. Why? That is what I'm going to explain now. To explain why, let's start with Taylor series. So we did a good review of Taylor series. I hope you reviewed the lecture notes and some question. There were 5 questions, and I think that's also part of the homework that you already submitted. So now you are comfortable with Taylor series. So this is the Taylor series expansion that I show in equation 17. and you're also familiar with how I started introducing Taylor series as fx is equal to fx0 plus x minus x0, f prime x0, things like that. Then at the end of the Taylor series lecture, I switched to this type of notation. Xi plus 1 is fxi times fxi plus the rest. We are expanding the function around fxi. So usually assumption is that xi plus 1 minus xi is, we usually assume it as a constant. We sometimes write it as x. We wrote it as h in the Taylor series lecture 4. So I'm sure this should be very clear to you, the expression I wrote in equation 17. So using that, we also reviewed it at the end of Taylor series. Xi plus 1 can be written as fxi plus f prime xi times xi plus 1 minus xi plus order of h squared. Why order of h squared? Yeah, I should have introduced probably here because h is xi plus 1 minus xi. So that is h. This is why it is order of h squared. Because the remaining term, the order of h squared represents as error. So the error, so this is the approximation on the left hand. So that is the approximation of fx plus. If you approximate fx plus 1 like that, the error will be in the order of h squared. Now using that, I can get a formula for, if you forget about order of h squared, then this becomes an approximation. What I show in equation 19 is an approximation. Up to equation 19, we did that. Actually, we, yeah, even we derived a formula for f prime x, that is fxi plus 1 minus fxi. In the previous lecture, we derived a formula for fx plus 1 as well. We derived a formula for f prime xi, sorry. Now, you are using the same to get xi plus 1 as a function of xi, that's all. So let me just for clarity, let me rewrite it. So from equation 18, that's from equation 19 should be very clear. F xi plus 1 is, instead of approximate, I am writing it as equal. Fxi plus f prime xi plus 1 minus xi. So all you have to do is just find what xi plus 1 in terms of everything else. So I will just subtract fxi plus 1 minus fxi is equal to f prime xi times xi plus 1 minus xi. Let me divide by let me see, I may make a mistake here. Let's see, plus 1. Okay, let's see. Give me a second here. So xi plus 1 minus xi is going to be f xi plus 1 minus f xi over f prime xi. So xi plus 1 is going to be xi minus f xi wait, xi plus, sorry, yeah, f xi plus 1 minus f xi over f prime xi. So what will happen to fxi plus 1? Did I write any notes there? Okay, so we are saying that if xi plus 1 is the root, I mean, so that's the assumption there. So if fxi plus 1 is the root, then this will be 0. So that is the big logic there. So if xi plus, sorry, that's not. If xi plus 1 is the root, then fxi plus 1 has to be 0. I mean, it all hinges on that assumption. So then we get xi plus 1 is equal to xi minus f xi over f prime xi. So that is the Newton-Raphson iteration. Again, it is an assumption. I mean, it is an approximate iteration, but it works really well for many applications. So that basically summarizes two of the method. Both of them are iterative method. All the methods for finding that we study iterative methods. It will start with an initial guess and keep on iterating until the percentage relative error falls below certain values, or until the maximum number of iterations are reached. Okay, so I will do an example. I'll do an example here on Newton-Raphson method. Where's the example? Here, okay. So we are taking the same example for Newton-Raphson method. Okay, fx. So fx is e to the power minus x minus x. Now the formula is xi plus 1 is xi minus f xi over f prime xi. So if we need to find those two, and then we had to make a custom formula for this particular example. For every example, there will be a custom formula. So if you make that, then everything becomes easy. But when you program, we'll talk about programming this a little bit later. Even here, when you program it, it is good to have a function defined. That way you can just go and change that function. That way you don't need to change anything else for your program. You can have a program for Newton-Raphson method. And if there's a new function, all you will have to do is change that function. Everything else will remain the same. So you'll use a pointer for that function. Okay, so f prime xi, we need to find f prime xi, which is a minus f prime x is minus e to the power minus x minus 1. So xi plus 1 is xi minus e to the power minus x over minus e to the power minus x minus 1. So that is xi plus e to the power minus x over e to the power x plus 1. But let me rewrite this. That would be xi plus 1 is xi plus e to the power minus xi minus xi over e to the power xi plus 1. Is that too confusing? Because here I just used x, but what they mean is, that we have to substitute a value for x. We will use the previous value. So So this is an iteration right there. That is, if you know the current value of x, so xi is the present value, present root. Xi plus 1 is the next root. So once you find xi plus 1, it becomes xi, and you just keep iterating it until you have to stop. When will you stop? When the epsilon a is less than a certain value, or when the maximum number of iterations is reached a certain value. So that's okay. So that's it for Newton-Raphson method. So let's see. So that's the algorithm there. Once again, it's the same type of algorithm. There's there's not much difference here. You need an initial guess. That's you need this algorithm will need an initial guess, and it will need the threshold to stop. So epsilon threshold. So then this formula will change for each example. For example, for this our example used in the lecture note, it came to this. But you can have a separate function in your program to store fx and find the derivative of fx, store fx and f prime x. Then nothing will change in your Newton-Raphson function. So each time you compute the percentage relative error, and then stop the iteration when epsilon a is less than epsilon threshold. Again, I did not show the maximum number of iterations here. I will probably add that. So that is your while loop. Okay, so that's all for the Newton-Raphson method, and there are some discussion about their convergence. It will converge nicely. For example, if you take this example, again, we are now looking graphically. So what graphically means? How does Newton-Raphson method works? So it starts with the present iteration, and then here you take the gradient of the function. So that is the gradient of the function at that point. So gradient or tangent of that function at that point, or tangent. And when the tangent intersects the x-axis, that is the next root. So that's the next root. So there's a geometrical way to represent this. So what is this height? That height is fxi. So fxi over, you can see fxi divided by xi minus xi plus 1 is what? That is the tangent at that point. So that is f prime xi. So from this, we can write fxi is f prime xi times xi minus xi plus 1. Now, from that, you can write xi plus 1 is xi minus f xi divided by f prime xi. So that is an alternate derivation. Here we did not use Taylor series at all. We just use geometry. So this derivation is just from what we see on this picture. what is gradient? The gradient is at this point, at that point, is written as f prime xi. Then the gradient can be using geometry written as fxi divided by xi minus 1. And then you just equate them, and you get the formula for Newton-Raphson method. So that's another way of looking at it. So, all of these previous method, there is a graphical way to look at it. I talked earlier about how fixed point iteration works graphically. It's a good way to understand it, even though we know the formula and we don't need this graphical interpretation to write a program, but it is good to know. It is good to know, especially to understand the limitations of these methods. So, similar to the fixed point iteration, the Newton method might also not work at some points. So that's what is shown here. Actually, this is not fixed point. Again, wrong in my lecture now. Figure 3 is indeed Newton-Raphson method. So we know graphically how Newton-Raphson method works. So let's take this example. So this is the initial guess x0. So we'll go to the function and we'll find the gradient and find where the gradient intersects. The gradient intersects x-axis at x1. Then the next iteration will be go to the function, take the gradient and find out where it intersects x-axis, that is x2. Again, go to the function, find the gradient. You can see this is the root. This is the root. We thought it will just converge towards the root, but it did not. It just keeps on diverging out of it, goes out of control. So this is out of control. So that is the point is the Newton-Raphson method. There are some cases where Newton-Raphson method won't work. Again, here's another example. This function has many roots. It is very wavy function. So if let's say you started here, that is your first root, and again it goes out of control. And so all the example here in this and in this figure show how it may go out of control. Whereas if you have a point like this, and then if you just start like this is your x0, and then the gradient, that is a gradient. So then that is x1, and then go here, and then you find the gradient, that is x2. You can see it goes really fast towards the root. That's the root. Sometimes the Newton-Raphson, for many functions, the Newton-Raphson method goes really fast towards the root, whereas some instances will diverge. So the summary is here we introduced two types of open methods. One is a fixed point iteration method. Other one is Newton-Raphson method. So for open method, you need one initial guess, x0. That is enough, and then there is a formula for each of them, and these are easy to remember formulas. There are 5 questions. I'll assign these questions as homework. Similarly, in lecture 6, bracketing method also, there are 5. If you just open the lecture 6 now, you will see there are 5 homeworks, 5 questions, but I will assign them as a homework as well. And then in the next class, I will finish the polynomial method for root finding. The polynomial method, one of the polynomial method is a little bit too complex. It is Very easy to, Newton method and the fixed point iteration method is very easy to remember. You know, xi is xi plus 1 is xi minus f xi f prime xi. Even if you don't know all the derivation, you can remember the formula. But you know, even if you had to derive, you know, all you had to do is think about the geometry and you can derive it. So fixed point iteration and Newton method are very easy to remember formulas. Whereas the next lecture, the formula, the polynomial method is a little bit too much to remember. I will mention that in the recording as well. So I will assign some homeworks, but definitely not. Well, this time there are no in-class lectures, so why not? If it is a take-home, I can assign because it is open book anyway. So that's all for today. But somebody's asking what is the midterm. So I announced this at the class early today. So midterm will be October 20. I'm going to give the midterm on October 20, Tuesday, after the class. And then you have time until the next class on Thursday, October 22 at 8:30 a.m. You need to submit it similar to homework. You will submit midterm through Blackboard. There will be a programming element in midterm, so which you will submit using Reply, I believe. Okay, so there was a question. Did somebody raise your hand? Any other questions? Yes, you have 2 days to do them, get the midterm done. So you will have very similar to homework. Midterm is very similar to homework, but there will be some programming questions too. Any other questions? All right, everyone. So that's you will see homework 5, 4, 5, and 6, and you will see lecture note for lecture 7. And again, we have a live lecture. I mean, quiz. We have a live quiz on Thursday. So quiz. So there's a quiz on Thursday. October 8 during class time.